Alright, so I copied this slide over from last week's presentation because I wanted to impress upon you how important it is to be familiar with these substances and the categories that they fall in, especially because the type of reaction that you expect to occur will depend on whether you have a nucleophile, a base, or something that could act as either a nucleophile or a base. Right, so we saw last time how the substitution and elimination mechanisms are in competition. So if I have one of these nucleophile only compounds, I don't really expect to see any significant competing elimination products. Oh, I'm sorry. Goodness. Thank you, Clayton. I forgot to hit share in my worry about the recording software. I forgot to share my screen. Alright, join in everybody. Jeez. Alright, so we were saying how these compounds that are really only effective nucleophiles and really weak bases, we only expect to see elimination reactions occurring. I'm sorry, not elimination. Alright, I gotta get things together here. Substitution reactions occurring, since they're only really gonna be acting as nucleophiles. One of these bases, if you forget what the structure of these look like, it's right here. These are bases. They're relatively sterically hindered, so they're not likely to come in and get all the way into the electrophilic center and do a substitution. They'll pretty much go for the beta proton, and these are all pretty decent bases. They'll pretty much most of the time result in an E2 elimination, because in the case of the H- it's very unstable. It needs to pick up a proton and balance its charge. And in the case of the DBN and DBU, when they pick up a proton, they're stabilized by resonance, and so they are actually pretty strong bases and pretty effective at picking up protons right away in the first step to push out the leaving group, assuming that you have a good leaving group. So here, these ones here are both bases and nucleophiles. So as we said, the main thing here that we're concerned with is sterics. The more sterically hindered my substance is, the more difficult it is for it to enter into the alpha carbon and push out a leaving group due to the steric hindrance. It'll be much more likely to go for a beta proton, which is on the surface of the molecule, much more exposed and able to be abstracted without much steric hindrance. So let's take a look today at some of the summary of what we're dealing with these categories. So as we said, nucleophile only, we really only expect to see substitution reactions. And as we talked about in Chapter 7, the mechanism, whether it be SN2 or SN1, will depend on how sterically hindered the site is that the leaving group's attached to. Right? A primary site's not very sterically hindered. So whichever nucleophile we have, we expect it to come right in there in one step and push that leaving group out in an SN2. And a tertiary site is too sterically hindered to do that. So if you have a nucleophile only, one of these compounds that falls under that category, the leaving group would have to leave first to produce a carbocation, then the nucleophile would come in a second step, so that's pretty much going to be SN1. And then in a secondary case, there's intermediate sterics. The leaving group could leave to produce a secondary carbocation. That would be a little bit unstable. So that's where we see the competing SN1 and SN2 both reasonably occurring. The degree to which one will occur versus the other will depend on sterics or how stable the carbocation is on that secondary carbon. So like for example, if it can be stabilized by resonance, that would favor the SN1, which, you know, the more stable the carbocation is, the lower the transition state is in that mechanism, the more likely it is to occur through that step. Right? So this is mostly Chapter 7 stuff. If we're dealing with the hydride, which virtually always acts as a base, or the DBN or the DBU, one of those two, those are also too sterically hindered to be nucleophiles, so they will pretty much only be acting as a base. Then we usually only get elimination. And We can't do E1 on a primary carbon, and we really won't see much E1 on a secondary carbon due to the instability of the carbocation. Now, we might see a little E1 if the carbocation is stabilized by resonance, but typically not so much. And even with a tertiary carbon, if my leaving group is on a tertiary carbon, even though it could leave behind a relatively stable carbocation, since these bases are pretty decently strong, as long as there's an alpha proton available that can get into an anti-periplanar position to the leaving group, so rotationally 180 degree torsional angle here, the base will typically end up getting involved right away because these are decently strong bases, and they'll usually start the process off and push out the leaving group, if I have a good leaving group, in one step. So pretty much I expect you to be doing an E2 mechanism anytime you have one of these three bases involved with a compound that has a leaving group, assuming that there is a beta proton that can rotate to an anti-periplanar position with respect to the leaving group. So if I have one of these compounds with a negative charge on oxygen, then I end up getting a mixture of mechanisms depending on sterics again. So with the tertiary compound, that's pretty clean. I should only see the elimination, right? As we said, the tertiary is too crowded for these to act as a nucleophile, even though they're also strong nucleophiles. The negative charge, it can't come in here. It's always going to be too crowded, even if it's a small, very small atom like an OH grouping to come in there. It's too sterically hindered. If it's a secondary, usually the sterics is significant, and so we still usually see more elimination than substitution, again, due to sterics. If it's a primary carbon, we might get some elimination, especially if I use a sterically hindered base. So like, for example, let's say my leaving group is here on a primary carbon. If I have a pretty sterically hindered base / nucleophile, since this primary carbon is not too crowded, I might get some substitution there. But if my base is really crowded, I might be more likely to rotate one of these hydrogens into the position anti to the leaving group and actually do an elimination. So the degree to which one is major and the other is minor, it depends on the specific molecules involved and how much steric hindrance there is. But what we're saying here is generally, most of the time, or on average, since a primary carbon is not very sterically hindering, we expect these oxygens with a negative charge, which are strong and unstable and need to start reacting right away. Usually there's enough space for them to come in right away and push the leaving group out and do the substitution rather than having to go for the beta proton. Right? When the leaving group is there, it's usually, well, it's always going to be more electronegative than a carbon, so it's going to create a fair amount of partial positive here, and that positive also helps to attract that directly in there. So as long as there's not too much steric, which is usually the case with a primary carbon, we usually see these negatively charged groupings attracted to that partial positive, pull it in there, causing the leaving group to leave, and doing a substitution reaction. But there are a lot of subtle things going on here, right? So in these instances where there's multiple mechanisms at play, you want to be familiar with the sterics and the strength of the acid and base and the likelihood of one mechanism occurring versus the other, so you can give a reasonable, detailed explanation in your answers on exams to explain why one mechanism is happening over the other and why one product might be more minor or more major than the other. And so then lastly, the fourth category is weak nucleophiles and bases. So these are when I have a neutral oxygen that's quite stable. So it's usually not unstable enough to usually come in right away and push the leaving group out. So we don't see very much direct substitution. We don't see very much direct elimination. In fact, those are happening, but they're in competition with SN1 and E1, where the leaving group would leave first because they're weak. That means they're relatively stable. So if I imagine the reaction coordinate diagram, if it's a stable reactant that doesn't have a charge that makes it very unstable, it starts at a pretty low energy. So for that to come in and push the leaving group out right away and do an SN2 with the sterics and the fact that it's relatively stable, it's a pretty high energy jump that it has to happen. So it's not going to happen very often. And since it's also relatively stable, to go in and pick up the beta proton and do an elimination, that can happen. But in the E2 mechanism, there's 2 bonds breaking, 2 bonds forming. The more bonds break and form, the more unstable it is during the transition state. So that also has a relatively high energy transition state. And so these are in competition with situations. As long as the carbocation is not too unstable once it forms, the SN2 and E2 are in competition with the SN1 and E1 because the leaving group might leave first, and then the reaction could occur. And so when I have all these mechanisms potentially occurring at the same time, giving me a mixture of products, these aren't usually reactions that we would run. If the reaction gives me a complicated mixture of products, I don't really usually want to run that reaction. I'd rather run a reaction that gives one set of products or maybe 2, and then I can easily separate the 2 using chromatography or something like that after the reaction. So we want to usually avoid these except for when we have a tertiary substrate for the most part. So let's just take a quick look at that. So let's say I've got tertiary leaving group here, and I've got SN1 and E1 in competition. So my base / nucleophile is relatively weak, so it's relatively stable. If it collides with this, most of the time nothing's going to happen. But if this thing collides with enough energy with something else, the loss of the leaving group could occur first. So that if that occurs, I would get a relatively stable tertiary carbocation, either way. So the first step of the SN1 and the E1 mechanism is the same. The difference is whether or not this comes in as a nucleophile. So let's just say we're dealing with water. The water would come in as a nucleophile if I were looking at an SN1. And that, let's imagine there was another proton transfer step after that to remove this proton. We saw some mechanisms like that before. Versus the elimination, where if I have the water, it can pick off one of these beta protons, and now that the carbocation is formed and the leaving group's gone, I don't have to worry about this proton being anti-periplanar to anything. Any proton could be picked off at any moment to complete that pi bond. And then the water would pick up that proton and become H3O+. So these steps are all in equilibrium. So what makes this process reasonable and practical is the fact that there's a different entropy on one product side versus the other. So in the substitution SN1 products, I have 1 molecule for every 1 molecule that I started with. It's a 1-to-1 ratio here. If I do an elimination by pushing out the leaving group and producing a pi bond, I also get this water picking up a proton, so I also get a second molecule. So for every 1 of these, I get 2 products. So when you do an elimination reaction, that process is favored by entropy, but the pi bond is not as stable as the sigma bond, so the substitution process is favored by enthalpy. This one is entropy favored. So what that means is I can control this with the temperature, because when I'm thinking about thermodynamics, enthalpy and entropy, I know that because of the way the signs work out in this equation, if I increase the temperature, the equilibrium will shift toward the side with more entropy. And if I decrease the temperature, it will shift toward the side with less entropy, if that side is favored by enthalpy. Right, so that's the situation we have here. So make sure you can get through that discussion and explain how, if the temperature were increased, because this elimination reaction involves a positive delta S, increasing that temperature makes delta G for that process more negative, favoring it. And on the other direction, the entropy change is very minimal, but since it's enthalpy favored, I would have a negative delta H, and that substitution product would be favored at a lower temperature where the entropy change doesn't really shift the process in that direction. And then, obviously, depending on the mechanism we talked about, there are different regiochemical and stereochemical outcomes. So once you determine if your reactant is a nucleophile or a base, and whether the substrate is primary, secondary, or tertiary, all those factors are determined. Those two things are the main things that determine whether you're dealing with an SN2, SN1, E2, or E1. Once you determine the mechanism, make sure you understand the regio and stereochemical outcomes of the mechanism. So this is just a summary of what we talked about in Chapter 7 and in Chapter 8. Right? So if I have an SN2, it has to occur by a backside attack. So I know the attack will occur at the alpha carbon where the leaving group was positioned, and I know that if it comes in from the backside from where the leaving group left, that may specifically produce one stereochemical outcome. If it's an SN1, the leaving group leaves first, but I still have that nucleophile attacking the alpha carbon, the carbon that the leaving group left from. But in this case, I get a racemization because once the carbocation is formed, it's a flat structure and an empty p, so the nucleophile can come in from the top to the bottom, and that's why spatially it will be positioned in one or the other direction. When we talked about the E2 in Chapter 8, we said there may be regiochemical concerns, right? And that depends on how sterically hindered the base is, right? So if you recall what we said about that was, if I've got something like this where my leaving group is here, and I've got one beta proton on one side and another on another side, and they would produce different products, the more sterically hindered the base is, the more likely it is for the available hydrogen. And that produces a so-called Hofmann product. If the base is not sterically hindered, it's more likely to go for the more crowded hydrogen. Why would it do that? Well, because when the electrons swing in, it starts to form a more substituted carbon-carbon double bond, or it's the carbon-carbon double bond that's formed is substituted with more carbon groups, so it's more stable during the transition state and after it forms. So that's the Zaitsev product. We can form that with a smaller base because it's more stable to form the pi bond in the more stable position with more carbon groups attached to it. Right, so don't forget about that consideration. And then when we form a double bond, we have the possibility of getting cis or trans. When that's the case, the trans double bond is usually more stable because there's less steric hindrance versus in the cis position. But we do have to make sure, if we recognize that each reaction is occurring, that only a beta proton position anti-periplanar to the leaving group can actually be picked off. And so that may determine what set of products you get, right? So you have to make sure if you're looking at the leaving group on one carbon and the beta proton on the other, they have to be 180 degrees torsionally, they have to be anti-periplanar. So whatever groups end up on the same side of carbon 1 and carbon 2 behind it would be cis, or on the same side of the double bond, and then these two groups over here would be on the same side of the double bond. So if there's only one available beta proton, you've got to think about what has to happen to the structure in order for that to rotate to an anti-periplanar position to the leaving group, and then whatever groups ends up on the same side in that rotation will end up on the same side of the double bond that forms, specifically if it's an E2 mechanism. If it's an E1 mechanism, then we're going to go through a carbocation. And once the carbocation forms, whichever beta proton produces a more substituted carbon-carbon double bond, that's the one that will be picked off. So if there are multiple beta protons, maybe here I've got some extra stuff attached, then I would expect the pi bond to form over here, because as it's forming and after it forms, it's more substituted with carbon groups than with hydrogen, and that would help to stabilize it. So that's why we always see the more substituted carbon-carbon double bond form rather than the other product. And we'll also, as the major product, virtually always see the trans to avoid the steric hindrance as well that forms during the transition state. Alright, so that's it for Chapter 8, other than discussing the quiz questions that kind of test your abilities with those concepts. So let's apply what we just talked about. So here, when it comes to determining the mechanism, the first thing I want to do is to look at the base/nucleophile and see if it's strong and see which category it falls into. So what we have here is an oxygen with a negative charge. That's unstable, so it's strong, but it falls in the category of being both a strong nucleophile and a strong base. So I don't know which way it's going to react. It's going to do a substitution, it's going to do an elimination. It depends on the substrate. And so what we said a minute ago was, if it's a primary substrate, unless this is an extremely sterically hindered nucleophile or base, I usually expect it to do a substitution. So I expect that to come in there and push out the leaving group one step because the primary carbon is not too sterically hindered, and because the chlorine, being electronegative, is creating a lot of partial positive there that actively attracts the negative charge into that site. So just to keep track of the carbons here, I've got 4 of them. And when this oxygen comes in, it's going to be bonded to the 4th one. And then I've got an ethyl group there, and then the chloride leaves, and obviously the sodium spectator ion is around still as well. So that would probably be the major product, and there may be a little bit of a minor product. The sterics here is not too much of an issue, so most of the time this oxygen would come in and collide directly with the alpha carbon due to its attraction to that partial positive, but there is a very small partial positive over here in this proton. So it could pick up that proton and do the elimination as well. And so if that occurred, that would pick the proton up. These electrons would swing in. And so in that case, I would get this set of products here, as well as the NaCl. But the pi bond's not as stable as the sigma bond. So that probably wouldn't be favored thermodynamically unless I turned up the heat, because it does at least form 2 products, and with more moles of products there's more entropy, and increasing the temperature would shift equilibrium toward the side with more entropy. But in terms of the kinetics, this product here would form more often because during the transition state there's not much steric hindrance, and there are fewer bonds breaking and forming when it comes directly in there, and so that should give me mostly substitution. In the second example here, I have a sulfur. So the sulfide takes, when we take a look at that, it's listed as a strong nucleophile. So it's got that negative charge. It's a bigger atom. We discussed how bigger atoms, those with their outer electrons in the 3rd or 4th energy level, are just much more likely to act as a nucleophile than a base. If it picked up a proton, it might donate that proton back because it would produce a stronger acid. So if the sulfide is around here, we expect it to react as a nucleophile, and since I have a secondary carbon and something that really is a nucleophile only, we expect it most of the time to come in directly and do an SN2. If it were tertiary, I would expect mostly SN1. But for the leaving group to leave first and produce a secondary carbocation, that's pretty unstable, pretty high energy transition state, and this nucleophile is not very sterically hindered. It's just 2 atoms. So for 2 atoms to squeeze in here and collide there, that's probably what we're going to see most of the time. That would produce the sulfide attached with a dashed wedge, because it has to come in from the opposite side from where the chlorine is leaving with the solid wedge. So that would be my major product. If the chloride did leave first to produce a carbocation, then the sulfide would attack half the time from the top and half the time from the bottom, because now it's flat. So if it attacks from the bottom, I get the same major product. So that would definitely be the major product. Again, mostly that. If a few of these leaving groups left first to produce a carbocation, and then the sulfide comes in from the top, I'd get a little bit of this minor product where the sulfide would be attached here. That would be pretty minor probably. And so by producing a set of enantiomers, even if this is the major one and that's what I want, I'd still have to somehow try to get rid of the other one if I need this in its pure form. So then in the third example, here I do have a strong nucleophile. It's also a strong base, so that oxygen with a negative charge is just as likely to come into a carbon as it is to a beta proton. In this case, though, it can't come into the carbon. So because it's strong, I expect it to get them reacting right away. So either E2 or SN2. But I can't do an SN2 because it's a tertiary carbon, so that's ruled out. Right? So I have to look at this substance reacting, whether it's strong or weak, and whether it's a base or a nucleophile, and I have to look at the substrate to see how crowded it is. There's a lot of things going into this consideration, so you should definitely practice a lot of these from the textbook. But in this case, a tertiary substrate, so you might say, well, the leaving group is going to leave first and produce a carbocation. But that's going to go through a pretty high energy transition state, and when I have a really unstable reactive molecule with a full negative charge, it's going to be colliding. It's probably more likely to get the process started by colliding since it's already pretty unstable. And so that would access whichever hydrogen here can rotate into the anti-position to the chlorine, and it would do an E2 mechanism for most of the molecules here to push out the chlorine, and that would produce this product here. Some of the OH molecules might attack at this carbon and push this pair of electrons in, but since that product is not substituted with as many carbons on the double bond as it is hydrogens compared to the other one, this is not going to, it's going to form through a higher energy transition state. It's not going to be as stable as N, so that would be a minor product. This would be major. And a few of the molecules might have the leaving group leave first, and then the OH comes in. So in a few of the molecules, I might actually see something like this form as well as a minor product. But when substitution and elimination are in competition, and I have a strong nucleophile slash base, if it's tertiary, I usually get mostly elimination because the substitution would require the leaving group to leave first, and the formation of the carbocation is not a very fast step. Questions about any of those? Okay, so now we can transition into talking about chapter 15. Chapter 15 is about spectroscopy, and this is a really powerful way to investigate the structure of a material you might have in the lab. So what you've noticed so far this semester is you can measure the melting point of a substance, or the solubility of it, or the boiling point, or the density. There's a lot of different physical properties you can measure to try to get an idea of whether a molecule has a certain structure or a certain identity. But those properties are not always easy to measure, and they don't really give you much certainty, right? There's a lot of liquids that have similar densities and boiling points. There's a lot of solids that have similar melting points, and if it's not pure, that can affect the melting point. So it's hard to use the melting point to identify it if you're not sure if it's pure or not. But spectroscopy is really powerful. It's a very powerful way of looking at the structure of a compound. So in spectroscopy, what happens is some type of light, thus the word spectroscope, is interacting, and by observing the interaction between the light and the molecule, it gives us some information about the structure of the molecule. And so that's what we're going to talk about. How to use these instruments that shine light through the structure to give us information about the structure. And so since light is waves of energy, or packets of energy called photons, and we know light can interact with electrons and with nuclei, and it can cause structures to move around, right? We know light is a form of energy. It can be converted to kinetic energy, and that can cause bonds to vibrate and rotate. So there's lots of different ways light will interact with matter, but we want to focus on specific ways that this occurs. So we can think of light as having both a wavelength and a frequency. So if you think about the light as waves, wavelength is the distance between the waves, and the frequency has to do with how often a wave passes through a point. Right? So these waves are flying through space at the speed of light. The more waves pass through some point in a given period of time, the higher the frequency. Right? So frequency is like frequently. How frequently do the waves pass through some point if it's flying through space? Is wavelength inversely or directly proportional to energy? Well, the answer here is inverse. Right? So the farther the waves are apart, the less energy there is. So one way you can think about this is to think of each wave as like a packet of energy. If they're all spaced out, it's not transporting as much energy as if they're much closer together. If each wave is a packet of energy, the more waves pass through some point at a given period of time, because waves all travel at the same speed, I have more energy there. So the shorter the wavelength, the greater the energy. The shorter the wavelength, the greater the frequency. So frequency and energy are directly proportional. The more packets traveling through a point at a given period of time, the higher the energy. The more frequently they pass through that point, the higher the frequency. So you want to have a decent understanding of some of this basic stuff that we're going to use as a jumping off point for understanding spectroscopy. So hopefully you're a little familiar at least with the electromagnetic spectrum. Our eyes can really only detect light in a very narrow part of the spectrum. In this section about spectroscopy, it's going to cover a couple chapters. We're going to talk about infrared light, and we're going to talk about radio waves, which aren't shown here, but they're on the lower energy side, even lower in energy than microwaves. So radio waves are going to be relevant when we talk about nuclear magnetic spectroscopy, and we're going to talk about IR spectroscopy as well. So these are all lower in energy than visible light. All right? We're not worried about getting hit by visible light. Visible light does not have enough energy to break up molecules most of the time or excite electrons into higher energy levels. And so these lower energy forms of light like infrared, microwave, radio waves, they're not dangerous. They're not going to break up your molecules or knock electrons out of your molecules. And so when we're talking about spectroscopy involving these types of light, we're not looking at how the light's going to break up the molecule, which is a huge advantage, right? If I've got some molecule that I made, like in lab 6, you're attempting to make the structure. If you want to know, did you make the correct structure? Some of you have been looking at TLC analysis, but the TLC analysis, most of you saw when you spotted benzyl chloride and your product, benzyl chloride spot went higher, and then there was a product spot that didn't go quite as high. So that doesn't necessarily tell us that the structure of the product is what we were trying to make. It just tells us that we have something in there that wasn't there initially. And so it's encouraging, but we really need some confirmation that this product is structured the way it is. So we want to use wavelengths of light that will interact with the matter, but don't have so much energy that they'll start breaking it up, right? If I've made this product and I'm going to use it for the next step or turn it into some pharmaceutical drug of some sort, I don't want to break it up. I just want to identify what it is. And so that's why we're focusing on wavelengths of light. Most of the analysis here will focus on wavelengths of light that interact with the molecule, and the way the light interacts gives us information about the structure. So as we said, we're going to focus on infrared spectroscopy first. UVVis is something you talk about a little bit in OChem 2. So we're not going to worry about that this semester. We're going to talk about NMR and IR for the most part. So let's talk about IR spectroscopy a little bit specifically. So we've already familiar, hopefully, a little bit with the quantum behavior of molecules. I think most of you have an idea of what quantum means at this point. But quantum means there are certain available levels. So, for example, if I have a tire rotating, it can rotate at any speed, and any kinetic energy. There's no unavailable speed. So that is not a quantum behavior. That is a continuous behavior. But molecules rotate or vibrate or behave in a quantum way rather than a continuous way. Right? So we know that, for example, when I rotate the bond between two carbons, if I have methyl groups that are anti to one another, that's a specific quantity of energy associated with that rotation. If I rotate the front carbon so that it's eclipsing its methyl group with the back carbon, that eclipsing interaction causes it to have a different energy. So there are certain energy levels that exist, and I can't have any possible energy there. If I want to cause this rotation to occur, I need a certain amount of energy. So only light with a certain energy or wavelength will be able to cause that rotation. And so, since matter has these wave-like properties for their electrons and this quantum characteristics where certain movement for the matter requires very specific quantities of energy to occur, this is really convenient for us because we recognize that if I use a certain amount of light and hit the structure with it, if the light doesn't have the right amount of energy, it might not cause the rotation. If it has the right amount of energy to overcome this repulsion between these groups when they start eclipsing, it might cause the rotation to occur. So we're thinking about this quantum behavior of both light and the quantum behavior of molecular rotation and vibration. And since certain energies are required to cause bonds to rotate, also certain energies are required to cause bonds to vibrate. So if I think about carbon-hydrogen bond, right, we talked about covalent bonds. We said there's a sigma bond there, and the electrons are surrounding nuclei, mostly in the area attracting to both nuclei. But if this bond were to stretch, well, then the orbital overlap would be minimal. And the electron density in between the atoms would not be as stable because it's not as close to both nuclei. So there's a specific energy difference between an optimal length bond and a stretched bond. And certain wavelengths of light will have the ability to stretch that bond. If the energy of light matches the energy difference between these two states, then the light can cause the bond to stretch. If it doesn't match, it won't cause the bond to stretch. Right? So that's what we're talking about when we're talking about quantum behavior here. Certain wavelengths or energies can cause molecules to move in certain ways. And by measuring those energies, we can tell something about the structure of the molecule. All right, so we talked about rotation and vibration. We'll talk about it since that's mostly what IR spectroscopy is all about. But just to review another example, we know that the energy of electrons is also quantized. And this relates to UVVis spectroscopy that we're going to talk about in OChem 2. But just to remind you of that from general chemistry as well, we know that if I have like a hydrogen atom with one proton and there's an electron and it's in the n equals 1, what has to happen for that proton, or for the electron, for the electron to move into n equals 2? Well, it has to absorb a certain amount of energy. Right? So it can't be anywhere between n equals 1 and n equals 2. We know that there are only certain energy values available for the electrons. And so when the electron moves from one energy level to another, there's a very specific quantity of energy associated with that. So that's what we mean by quantized. I can't move the electron, one tiny bit out. It either is in n equals 1 or it's in n equals 2. There's no in between. And that type of behavior is also true for rotation of bonds, which is more Microwave radiation causes rotation of bonds. It's also true for vibration of bonds. So if I want to stretch a bond or bend a bond angle, that requires a very specific quantity of energy. Not just any old quantity of energy will do. And so that's really convenient because we can take advantage of how the quantity of energy relates to the types of bonds that are present, and that gives us information about the structure of the molecule. So each different type of bond has different vibrational energy levels, and they're separated by gaps because they're quantized. Right? So when the bond is shrinks or expands, there's a specific quantity of energy difference between those two states. You have to think about a CO double bond. If it shrinks or it expands, the stretching of the bond, shrinking and expanding, shrinking and expanding, there's a specific energy difference between those two states. So to get that bond to vibrate and stretch like that, it requires a very specific quantity of energy. And only a specific wavelength of light will have that energy. So what we see is when your structure has a carbon-oxygen double bond in it, it will, and other molecules that also have carbon-oxygen double bonds, they'll all absorb light at a very specific wavelength or frequency, because that's the frequency that causes that bond to stretch. And so when light hits that, instead of the light passing through, as it stretches the bond, now the bond is and it's less stable, it's higher in potential energy. So the light energy gets converted to potential energy. When the bond stretches, it also causes the bond to actually move, and so the movement is an increase in kinetic energy. And so a very specific quantity of light will be converted into other forms of energy, and it won't pass through the material. And so that's what we're talking about here. When the light strikes the molecule, if that light has the exact amount of energy needed, it will cause the bond to stretch or bend. And so since that energy is no longer in the form of light, now it's in the form of kinetic energy, stretching or bending, that means that that light doesn't pass through the sample. Eventually it's released in the form of heat, right? Because as we said, bending and stretching is molecular motion, and when molecules move around more, whether it's vibrational, rotational, translational motion, those all produce an increase in temperature or an increase in heat. But the key thing here is that since it's the light that's causing the vibration or motion, the light is converted, it's absorbed and converted into a different form of energy. So when I have my sample and I shine light at it at a specific wavelength, if that light gets absorbed and nothing comes out the other side, there's nothing coming out the other side, that tells me that that structure, that molecule must have had a certain type of bond that absorbs that specific wavelength of light. And so I'm going to shine a whole bunch of different wavelengths in. They're all going to be in the infrared part of the spectrum, but some will have slightly shorter wavelengths, some will have a little bit longer wavelengths. Depending on which ones get absorbed, that tells me which bonds are present, because each bond absorbs a different quantity of energy to cause that bond to stretch or bend. And so that's the basics of infrared. And so we want to talk about some specific bonds and how they bend and stretch. So there's really a few different types of vibration. We said there's stretching, and so that's like thinking of the bond as like a spring, where it can get longer or shorter. So stretching increases the bond length and decreases the bond length. Each type of bond between any two atoms, whether it be carbon, hydrogen, or carbon, oxygen, or whatever, each type of bond requires a different amount of energy to cause it to stretch. There's also bending. So if the bond angle here gets shorter or longer, so normally at a tetrahedral carbon it's like 109.5, but it might compress to like 95 and then expand to a little bit larger. That bending motion requires an absorbance of a specific amount of energy. Bending frequencies are usually lower in energy than stretching. And there's a lot of different ways molecules can bend. So not only can the bond angle increase in the plane, but there's also out of the plane bending. So if this atom here comes out at you for a second with a solid wedge, and this atom starts to move behind the screen with a dash wedge, and then they switch, and now this one's coming out at you, and that one's going behind. So that would cause a different type of motion, which means it absorbs a different quantity of energy. And so for whatever molecule I have, there's lots of different ways all the bonds can bend in plane and out of plane. So there's always going to be lots of wavelengths of light that are absorbed to cause this bending to occur. And that makes it difficult to interpret, right? When whatever molecule I have is absorbing all kinds of different wavelengths in these low energy parts of the spectrum, it's hard to really tell what the molecule is with much certainty. So we're going to focus more on the stretching frequencies, because this tells us really what type of bond I have. If I have CH bonds, if I have OH bonds, I can usually tell which elements are bonded by which wavelength of light was absorbed to cause the specific stretching of that bond. We also know objects can emit infrared light. And that's what happens when a moving bond slows down, right? So if I have like a CH bond that's stretching, it's already been hit by light, or it's already been involved in a collision, and it's absorbed some energy, and the bond is getting longer and shorter. It's already in the process of moving, so it's stretching a lot. If it stops to stretching so much and the bond slows down, so this would be faster stretching, this would be slower. If it's not stretching so much, it doesn't have as much kinetic energy, that state of having more kinetic energy to not moving as much, so there being less kinetic energy, that kinetic energy can be lost and translated or transformed into usually infrared light. So this light is created from kinetic energy that existed previously. Right? So we know different forms of energy can be converted into one another. We can't create or destroy energy out of nothing. But if I have motion, molecular motion, which is a form of kinetic energy, and then the molecule slows down because some of that energy is released in the form of light, usually it's infrared light that's released when molecular motion slows down. And that's how night vision and certain medical diagnostics work. Right? So we see different quantities of infrared light in the areas that are warmer, and different, and we don't see as much infrared light in areas that are colder, because the warmer objects are just constantly cooling down and slowing down, and they're emitting some or converting some of that kinetic energy into infrared light that's emitted. So we know infrared light can be emitted from hot objects, and we know objects can absorb infrared light, which causes them to increase their heat or increase their motion. And so we're going to be focused more on absorbing light, because we're interested in determining the structure of chemical compounds. Right? I did a chemical reaction. I want to know if the reaction worked. Supposedly my reaction converted maybe this benzyl chloride into this ether here. So what are the differences? Well, in one I've got carbon-chlorine bond. In the other I've got carbon-oxygen bond. So the different types of bonds will absorb different frequencies of light, infrared light. And if I shine light through there, and initially I see certain frequencies being absorbed, then later I see different frequencies being absorbed, that can give me a clue about the reaction, the success of the reaction. So, how much energy will a bond absorb? Well, if we're specifically talking about stretching the bond, it depends on the mass of the atoms involved, as well as the strength of the bond. So it turns out that the atoms with less mass require more energy to stretch. The smaller atoms require more energy to stretch. Right, so there's a bigger energy gap when I stretch a CH bond than when I stretch an OH bond. And this is all experimentally verified, right? I can get compounds that don't have any CO bonds. I can just look at methane if I want, where all the bonds are CH bonds. And I can look at what wavelengths of light are absorbed. I can shine all the different infrared wavelengths at this molecule, and when some of the wavelengths are absorbed, it causes bond stretching. I can measure the energy difference. I can measure that by measuring what wavelength of light was absorbed. And if I look at a molecule as a CO bond, I can see there's a different quantity of energy absorbed to cause that bond to stretch. So scientists looked at this in detail, and they developed some equations and some relationships that we can discuss here in a minute that relate the type of bond to the amount of energy absorbed. But first I wanted to explain how the instrument works. So as we said, you're going to put your sample, usually it's deposited neat, which means pure, on a salt plate. And why are we using salt? Well, there are no covalent bonds in salt. So this salt plate is usually like a little disc. And this little disc is made out of salt. So all that's in there is Na plus, Cl minus. They're not covalently bonding. They don't have a covalent bond to stretch. So when the infrared light passes through that salt plate, there shouldn't be any light absorbed. It should all pass through. So what I'm going to do is I'm going to take my sample, I'm going to put a droplet on there, and when the infrared light passes through that droplet, some of the wavelengths will be absorbed. So I'll be passing through all the frequencies of infrared light. The ones with slightly longer wavelengths, the ones with slightly shorter wavelengths, they're all passing through that. They're all shining into that sample. And when only certain ones pass through, the machine will measure that, and the machine will know all these wavelengths were shot at this sample, but only certain ones made through. So the other ones that didn't make it through must have been absorbed. So the machine determines which ones didn't come out the other side. It knows those were the ones that absorbed, and then it produces a picture of all the wavelengths that were absorbed, so we can use that to determine what types of bonds are there, because different types of bonds absorb different amounts of light, or different wavelengths of light. All right, so that's the basic idea there. So here's what one of the spectra looks like. So the way the units look here is we have percent transmittance on the y-axis. So 100% transmittance means all light made it through. 0% transmittance means light was absorbed. So here we're looking at peaks that come down from the top. And if I put my sample in here and there was no compound on it, if I just use the salt plate and I put that in the instrument, I should basically see a line that just goes to the top. Because all the light would shine, it would be 100% transmitted through the salt plate if there's nothing there to absorb it. So what I'm seeing here is light at this particular frequency at about 3,400 wave numbers, which we'll talk about in a second. That light was absorbed. That means there's something in the chemical on that salt plate that has certain type of bond that absorbed that light, and the light's no longer there. Now it's causing the bond to move, stretch. And then there's also something a little below 3,000. Some bond in my material is stretching because it absorbed the energy coming through at that wavelength. Over here, there's nothing in the bond that's causing, there's nothing in the compound I put in my salt plate, there's nothing to cause that light to be absorbed. So it shines right through. So that tells me whatever type of bond might have absorbed light at this energy, it's not there. So I can tell generally what type of bonds are in my compound, and also rule out other certain types of bonds in my compound. So here, typically, for example, if I had a CO double bond, that stretching of that particular bond would usually appear around 1700, and so I don't really see a peak there. So I've got something tiny up here, but it's probably an impurity. I would see a big peak here if the CO bond were present in my molecule, because it would absorb most of the light in that particular frequency. And so the fact that I don't see a peak there tells me that the light shined through, which tells me that that bond was not there to absorb the light. So the wave number units on the bottom here are basically measuring frequency. This is really the equivalent of 1 over the wavelength. That's why we have inverse distance units, right? We said wavelength is the distance between waves. Inverse distance would be 1 divided by wavelength. So we're dealing with frequency. And we said the relationship between frequency and energy is the higher the frequency, the higher the energy. So what we're saying here is the bonds that are absorbing these wavelengths of light require larger quantities of energy to cause that bond motion to occur. And so there's a cutoff right around 1500 here, where the energy below this, so this is low energy, and this is higher energy. This is mostly the bending vibrations, and this is mostly the stretching. So that's why we said earlier, there's almost always, no matter what my organic compound is that I run through the infrared spectrometer, I'm always going to see a bunch of peaks in here. And it's hard to tell what any of them mean, because there's always a whole bunch of them, because there's always CH bonds and CC bonds, and those bonds can bend in and out of planes. So there's lots of different bending motions, and each one of those motions absorbs a slightly different wavelength of light, so I see a whole bunch of peaks in there. And it's hard to interpret what any of them mean. Alright, so we talked about that. So when you get an IR spectrum, there are really 3 important characteristics of the spectrum. One is the wave number, right? So we talked about that a little bit. We said the higher number, the higher the amount of energy being absorbed, and each different type of bond absorbs a different wavelength or frequency or energy of light. So when I see absorbance around 3000 or around 3400, that tells me specific types of bonds are present absorbing those specific wavelengths. We also need to look at the intensity, right? So this one peak here was very small. If it was here, that would have meant something different. So the strong signal that's very big and absorbs a lot of light versus a weak signal that's very small, only absorbs a tiny bit of light. Often the weak signals don't really mean much. They may be an impurity that's present, or a bond that's not very polar. So we'll talk about intensity of the signal and how that, or the strength of the peak and how that relates to the polarity of the bonds. And there's also shape, right? So notice some of these signals, like this one here, is pretty sharp, versus this one here is a little broad. It's a wider sized peak. And so we'll talk about what the shape of the peak tells me about the molecule as well. So there's a lot of information here in terms of where the peak shows up, how big the peak is, and how broad the peak is, that we can use to determine some information about the structure of our compound that we're analyzing. So let's talk about these one by one. So the first one here is the wave number. We're going to talk about this one first. We talked about it a little bit already. We said there is an equation that can be used to calculate the wave number. We're not going to be expecting you to do any math with this equation at all. It's only here to point out the 2 factors that affect how much energy is required to stretch a bond. So specifically, we're talking about stretching here. This is just for stretching, not any of the bending stuff that we just mentioned that we're not going to focus much time or effort on. So if I increase how strong the bond is, stronger bonds require more energy to vibrate. Right? So for example, a CO single bond versus a CO double bond, which is a stronger bond? Well, here I have a sigma. Here I have a sigma and a pi. Two pairs of electrons attracting those nuclei together. So this bond is going to be stronger. So it's going to require more energy to stretch. The stronger the bond, the greater the energy required to stretch it. Another factor that affects the energy required to stretch a bond, though, is the mass of the atoms that are sharing electrons. So if I have a CO single bond or a CO double bond, this factor makes no difference. If I multiply the mass of the carbon times the mass of oxygen, multiply them together, and then divide by the mass of carbon plus the mass of oxygen, that would give me the reduced mass. So we're not going to necessarily work with the numbers or plug anything in here and get any values or quantitative calculations here. We're just pointing out that if I have two bonds, the strength of the bond and the mass of the atoms involved affects the energy required to stretch that bond. So the heavier the atoms, when I multiply them, I'm going to get a large number, and then atom, the number's not going to be as large. So the reduced mass that I get is going to be a larger value with heavier atoms. So it's going to be larger if the atoms are heavier or have bigger masses. But this is on the bottom of this fraction. So when I divide by a larger value for heavier atoms, it means actually less energy is required to stretch that. So we said that earlier. The heavier the atoms, the lower the energy needed to stretch them. So if I'm looking at a CO bond versus like a CH, the hydrogen is less heavy than the oxygen. So when I calculate their masses and the strengths of the bond and plug all that in, what I find is the CH bond vibrates at a higher frequency or requires more energy to vibrate than the CO. Right, so we're not going to have to work with this equation. This work's already been done for us. We're mostly going to focus on just kind of learning which types of bonds will produce signals or absorb energy of certain values. So if I have, just to answer this, if I have heavier atoms, it will require a lower number to stretch that bond. And so here are some specific examples that illustrate that, right? So these experiments, this equation is not some amazing thing that someone thought of and then they happen to find out that it was correct, right? This is an empirically or experimentally determined equation. So you do a bunch of experiments where you measure what wavelength is absorbed depending on the type of bonds that are present in the compound. And so if we swap out a hydrogen for deuterium, what's the difference? Well, hydrogen and deuterium are the same element. The only difference is the deuterium is a little heavier because it has one proton and one neutron versus the hydrogen with just a proton in its nucleus. So with the extra mass, it absorbs a lower energy form of light. The bond of the strength of the bond is basically the same because it's the same element. But the heavier mass lowers the energy required to stretch that bond. And so we see the same thing here. Carbon-oxygen versus carbon-chlorine, similar strength in the bond, but the lower frequency required to stretch the bond when the elements are heavier. So one of the limitations of IR is it's really hard to tell if you have a carbon or a chlorine or a bromine or some other heavy element present. Right? Because what do we say? Around 700, that would be right around 6. So this would be 700 right around here. Well, there's always peaks in that area due to bending vibrations. Well, if I have a peak there due to some bending vibration, and then I also have a peak there due to the stretching vibration, I don't know, it's hard to tell what's going on. So it's hard to use IR to definitively determine some of the bonds that might be present. And the same thing here, 1100, if I have a carbon-oxygen or carbon-nitrogen single bond, in the 1100 area, which is right around in here, there's always some peaks there from bending frequencies. So I can't really tell whether my molecule is a CO or a CN single bond from IR. But any of these signals that are above 1500, when I look at a spectrum above 1500, there's usually nothing here, unless the molecule has these specific types of bonds. And when we see a peak in a specific area, that can give us some pretty definitive information that our molecule has specific types of bonds present. Right, so that's the idea here. So this shows a summary of the kind of things we're looking at. X here could be carbon, oxygen, nitrogen, and those are the main ones. So if I have a carbon, hydrogen, hydrogen, the low mass hydrogen atom means that it's going to be a higher energy stretching. So somewhere usually around 3000 or higher for those types of bonds. Triple bonds are relatively strong, so even though the bond is strong, with the heavier atoms than the hydrogen, it's going to be a lower energy vibration. But stretching a triple bond usually requires a specific quantity of energy. So usually I won't see any signals between 21 and 2300. But if I do, that's a strong indication that my molecule has a triple bond in it. Double bonds usually appear between 16 and 1800. And then, as we said, the single bonds are difficult to really pinpoint because their stretching frequencies overlap with bending frequencies, and that causes a lot of difficulty in interpreting what's happening in that region. So the region above 1500 here is called the diagnostic region. And that's because we can diagnose what types of bonds are present depending on where we see peaks. The area below 1500 is called the fingerprint region. There's always a bunch of peaks there, but the specific pattern of those peaks could potentially be matched up with the pattern we see for a specific molecule. So if you can go online, for example, and find out what the IR spectrum for a molecule you've made should actually look like, and then you get the IR spectra that you experimentally measure for the molecule, and you can match up the fingerprint regions, that can really be helpful in identifying the substance. But we're going to focus more on the diagnostic region as far as exam questions and things like that go. So here's an example structure for an example molecule. So here I have this OH bond here. And here's the IR spectra. So what am I seeing here? Well, I've got a signal here. This one happens to be for the OH stretching. This grouping of signals, so it's kind of jagged down here, and there's like a peak here and a peak here. If I see multiple peaks right in the same area, that's likely because I have different types of bonds that are very similar, and that's what I have in this structure. I've got a CH bond of this type. The CH bond here is a little bit different. The CH bond here is different. The CH bond here is different. So each of the CH bonds is producing a signal, and they're all adding and stacking on top of one another. That's why I have such a big, strong signal here. And that's why there's a couple different ones, because there's the different CH bonds require slightly different quantities of energy to stretch. And then there's really nothing else in the diagnostic region. And so that means any type of alcohol like this, so even if I had a different alcohol structure, maybe it looked like this, or maybe there's branching over here, whatever the structure looks like, if I have an OH in my molecule, I'm going to see a signal for the OH bond. If I have CHs in my molecule, which there are pretty much always CHs in an organic compound, I'm going to see a signal around 3000 for all the different CHs all absorbing infrared light roughly with the same amount of energy almost. I can tell because there are no real signals in this area between 1500 and 2500, I can rule out there aren't any triple bonds in my structure. There aren't any double bonds in my structure that would normally produce peaks due to stretching. So I can match the structure with the spectrum, but not exactly, right? So let's just number these carbons 1, 2, 3, 4, and let's take a look at what it would look like if I had a slightly different molecule. So instead of a 4-carbon chain here, I only have a 3-carbon chain. What's the difference? Right? This spectra looks different from that one. Not by much. So both spectras have the OH for the OH bond. Both spectras have some CH. Both molecules have some CH stretching that's occurring around 3000. And then I don't see anything in the diagnostic region for either one, but then they each give their own individual fingerprint region. And that look kind of similar, but a little bit different. So there are definitely some differences. If I know what the fingerprint region should look like, I can kind of match it up with one of these two and identify the substance. But overall, when two molecules have the same type of bonds, their IR spectra are going to look really similar. And so that's where we're seeing the limitations of IR. IR is very good at telling you the types of bonds that are present, but it's not very good at telling you the exact structure of the molecule. And when I have two molecules that are similar in the types of bonds they have but are not identical, clearly these two structures are different, they have different formulas, IR is maybe not the best way to identify which one I have. Unless I know the spectra and I can match up the fingerprint region. But even that can be a little bit tricky. So we're going to talk mostly about how to use IR to determine the types of bonds that are present. And again, that mostly will have to do with the wave number that you observe. Right? So what we saw here is the OH stretch versus the CH stretch. The OH stretch comes a little bit higher in terms of the higher frequency or higher energy light required to stretch that bond versus the slightly lower energy of light required to stretch that bond. And what's the difference? Well, the carbon isn't quite as heavy as the oxygen. So with the heavier oxygen, that should increase this value and actually decrease, because I'm dividing by a larger number, it should decrease the frequency of light required to be absorbed. So if the CH bond and OH bond were equally strong bonds, the OH stretch would be at a lower wave number than the CH stretch, but that's the opposite of what we see here. So that tells me that the OH bond must be stronger. Even though this number increases a little bit, this number must increase even more. The stronger OH bond requires a higher frequency of light to stretch. All right, so this also gives us information about the strengths of bonds, which helps confirm other measurements of bond strengths. So let's take a look at the CH bond, right? Because if we're organic chemists, we're really concerned about carbon. And all of our molecules that we might make have carbon-hydrogen bonds, at least somewhere in their structures. And what we find is, if we do some experiments, is that if a carbon is sp3 hybridized, its CH bond stretches if it absorbs energy that's slightly lower than the energy required to stretch the CH bond if the carbon's sp2, which is a little bit less energy than what's needed to stretch the CH bond if the carbon's sp. So what we're recognizing here is it's the same type of bond in each of these cases, but the amount of energy required to stretch that bond is a little bit different. Okay, so we're not talking about stretching the carbon-carbon bond. Clearly there's a difference in the strength between a carbon-carbon single bond, carbon-carbon double, or carbon-carbon triple bond. Right? The more electrons we have, the more tightly they're held, the more energy would be required to stretch that bond. That's not what we're talking about here. We're talking about the CH bond. Carbon-carbon bonds appear lower down on the energy side because those are heavier atoms. So the differences here, are they due to mass or bond strength? Well, obviously they're not due to mass, right? carbon, hydrogen, same mass as carbon, hydrogen, same mass as carbon, hydrogen. The difference must be the bond strength. So which of these bonds is stronger? Why would one CH bond be stronger than another? Well, it has to do with the type of orbitals that are involved. Right? So when my carbon is sp3, an sp3 orbital is more elongated versus a carbon with an sp2, a little bit more compact, versus a carbon with an sp, and these are exaggerated versions of the shapes, but the sp is even more compact. So when the hydrogen comes along with its 1s to overlap there, the more compact the carbon's sp, sp2, or sp3 orbital, the more effective the overlap, the closer the two get, the more the electron density can get close to both nuclei and form a stronger attraction. So when the carbon's orbital that's overlapping with the hydrogen is more compact and the electrons can get closer to both nuclei, it's a stronger bond and it requires more energy to stretch that bond than it would be if the orbitals were a little longer. So this is really useful to us. We can tell what types of CH bonds are in our structure by looking at what wavelengths of light are absorbed when we put that structure in the IR spectrometer. And so here's some examples of some molecules that would produce those signals. Right? So if my molecule doesn't have any sp2 or sp3 hybridized carbons with hydrogens on them, I won't see any peaks above 3000 because all the CH bonds on sp3 hybridized carbons are a little bit weaker and they only absorb energy below 3000. And so this 3000 is a nice cutoff. It's a really nice, useful way to look at what types of carbons are in the structure. If all the carbons that have hydrogens attached to them are sp3, then all those CH stretching will only absorb energy below 3000. If I see a peak around 3100 or between 3000 and 3100, that usually indicates a CH on an sp2 hybridized carbon. Because it's a little bit stronger a bond, it requires a slightly higher amount of energy to cause that bond to stretch. And when it's an sp hybridized carbon and the orbital overlaps, even pulling the electrons closer to the nuclei, it takes even more energy to stretch that, specifically closer to 32 or 3300 wave numbers of energy to stretch that bond. So that's the first thing you want to look for. If you get an IR spectra, look around 3000, see if you see a couple signals just above 3000 or if all your signals are below, and that can tell you whether or not you have an sp2 or sp3 hybridized carbon, specifically with a hydrogen bonder to it. So let's practice that skill a little bit. Alright, so how many signals would be produced above 3000 for each of these structures? So let's take a look at this first one. How many signals above 3000 would we see here? Well, what we see is when we're looking around 3000, we're looking at the CH bonds, not the CC bonds. And a lot of students make that error. So try to make a mental note of that and as strongly as possible for yourself. The CH bonds are what come around 3000, either just below or just above. So all the CH bonds here should all be below 3000 because these are all sp3 hybridized carbons. This sp2 hybridized carbon does not have a hydrogen attached, so it will not produce a signal above 3000. It's not the carbon itself, it's the CH bond. So when I have a CH bond on an sp2 hybridized carbon, that one should be above 3000. The other ones will be around 2900. All the other CH bonds for this first structure. What about the second structure? Will the second structure produce any signals above 3000? Well, each of the sp2 hybridized carbons has no hydrogen. There are hydrogens here, so these CH bonds will be producing signals around 2900. but nothing above 3,000. Oh, right, there's an OH bond. So the OH stretching, that usually occurs around 3,400. So there will be a signal above 3,000 for the OH stretch, but there will be nothing around 3,100 for a CH stretch. So just because I don't see a signal around 3,100 doesn't mean there aren't any sp2 hybridized carbons. It does mean, though, that neither of those carbons has a hydrogen bonded to it, because if this were like a hydrogen bonded to that, that bond stretching would occur around 3,100. So the fact that there's no hydrogen bonded to either of those tells me that I don't expect to see any signals above 3,000 other than the OH bond stretch signal. And that's what we see in compound 3. Nothing above 3,000. Each sp and sp2 hybridized carbon does not have any hydrogens. The only hydrogens here are bonded to sp3. And so if the only type of CH bond is on an sp3 hybridized carbon, I only expect to see signals around 2,900, nothing above 3,000. So make sure you can answer questions related to that. Another type of signal that's very common, because CO double bonds are very common, is the signal around 1,700 for the carbon-oxygen double bond stretching. Right, so we said double bonds usually come between 1,500 and 1,800. Specifically, carbon-oxygen double bonds are the most common type of double bonds, other than maybe carbon-carbon double bonds. So carbon-oxygen double bonds, very common functional group, and they produce a signal usually around 1,700. So to stretch this bond, less energy is required. It's a relatively strong bond, but the elements are relatively heavy compared to like a CH or an OH. The lighter elements are the higher energy stretches. So this is a lower energy stretch, but at least it's above 1,500, so we can usually find it if it's there. Right? So let's just go back here and look at a couple examples. So there was nothing here around 1,700 really to speak of, and that confirms there's no CO double bond in our spectra. Those signals are usually quite strong. The CO double bond signal is usually quite strong, which we'll see why that is in a minute. And the resonance, the resonance aspect of that is not super relevant to what we need to get into, so don't worry about that too much. The resonance can affect the exact positioning, but that's a little bit more detail than I would ask you about or expect you to get into. So that's pointed out here. So you know, this pi bond can shift up here, this one can shift up here, and when it does, this one can shift over. So there's more resonance, which stabilizes the situation a little bit and affects the wave number a little bit. Right? So I don't expect you to know specifically for a CO double bond versus a CO double bond with a pi bond near it versus a CO double bond with an oxygen versus one with a pi bond and an oxygen. The exact wave number will vary a little bit, but they're all pretty close to 1,700. So really what we're looking for here, I'm looking for you to be able to identify something between 1,650 and 1,750. If you see a big signal in that area, that's an indication of a CO double bond. That's pretty much the extent to which you need to be familiar with IR signals related to carbon-oxygen double bonds. All right, so that covers the basics of wave number. Right? Wave number tells me where on the scale the signals appear. Right? So what you need to know about wave number is the stronger the bond, the higher the wave number. The lighter or less mass of the atoms, the higher the wave number. There's a specific difference between the wave number when it's a sp3 hybridized carbon hydrogen versus sp2 carbon hydrogen versus sp carbon hydrogen. That you definitely need to be quite familiar with. You need to recognize in general that OH, CH, NH stretches occur on the highest wave numbers. Triple bonds, slightly higher wave numbers than double bonds, and then single bonds we're not going to worry about too much because those are all overlapping with the bending frequencies. And then specifically the CO, since it's so common, between 1650 and 1750, look for that. Alright, so we're also interested in signal strength, because if a bond absorbs a lot of infrared light, it will give a very strong signal, because very little of the light will pass through if it's all absorbed by the molecules. If a weaker signal is formed, that indicates that the molecule is only able to absorb a little bit of light in that particular frequency. And so we want to try to understand what causes more or less light to be absorbed. And the answer is bond polarity. So the more polar the bond, as it stretches, it creates this oscillating dipole. Right? So if we think about a polar bond, like for example a carbon-oxygen bond, when the bond is shorter, right, so due to the electronegativity difference, there's a partial positive and a partial negative. Same thing if the bond is longer, so if it's a little stretched, I still have a partial positive, partial negative. But the dipole, the degree to which that polarity exists, or how polar the bond is not just affected by the quantity of charge, it's also affected by the distance. So the more farther apart the partial positive and negative are, when I multiply that by the quantity of partial positive and negative, that's what really determines the magnitude of the dipole. So this is a less polar bond, and this is a more polar bond. We don't really think about distance very often. When we're looking at bond polarity, mostly we just think about what's the electronegativity difference, right? The more electronegative one atom is compared to the other, the more polar the bond. And that's the major factor that affects the polarity of the bond. But the length of the bond is also affects the polarity. So if I have this CO bond and it's stretching, it's getting longer and shorter and longer and shorter over and over and over again. When the bond is stretched, the dipole increases. When the bond is compressed, the dipole decreases. So as it's stretching, it gets longer and shorter and longer and shorter over and over again, like a cycle. And that causes its dipole moment to be increased and then decreased, and then increased and then decreased. And that is absolutely key to the success of infrared spectroscopy. It's this oscillating dipole where the bond gets more polar and then less polar and more polar and then less polar as it gets longer versus shorter. That's what the oscillating dipole is, that interacts with the light energy as the light is passing through the sample. So if I have a very polar bond, it's going to have an even greater dipole difference, right? When the bond is very long, it's going to be very polar, and when it's very short, it's going to be less polar. If I have a less polar bond, then the difference is minimal. And so the larger this difference is, or I should say the more the dipole oscillates from very polar to less polar, the more the dipole changes, the more it absorbs light. And so that's just a phenomenon that's observed. And so what that means overall is that the greater the bond polarity, the stronger the signal. The more polar the bond, the bigger the difference in the dipole when the bond is stretched versus compressed. And the more light it will absorb. Right? So what we're seeing here is, this is a strong signal. This is an indication of a polar bond, probably like a CO double bond or something. Because that bond is so polar, when it stretches, there's a big difference in polarity, And that is what allows it to absorb a lot of light. Very little light makes it through that isn't absorbed by the molecule. If I have a less polar bond, maybe like a carbon double bond, if the carbon-carbon double bond is symmetrical, it won't be polar at all, and I won't see the signal at all. It has to have some degree of polarity. So maybe there's like a chlorine over here or something that's attracting some electrons. So this side is a little bit more positive, and this side over here maybe it doesn't have as much of a charge. Maybe it only has a tiny positive. So if there's any difference in the quantity of charge on the two carbons, when that bond is stretched, the difference is magnified. And when it's compressed, the difference is minimized. So that means that if the bond is slightly polar, it will produce a slight signal. If it's highly polar, it will produce a very strong signal. And so that is why we typically see CO double bonds as very strong signals somewhere between 1650 and 1750. If you see a very small signal or more medium-sized signal in that area, that's probably not a CO double bond, because the CO double bonds are so polar, they almost always produce massive signals, because the more polar the bond, the more light is absorbed. So let's just imagine a symmetrical molecule. So let's say we have 2,3-dimethyl 2-butene. So if I have bute, it'd be 4 carbons. If I have 2-butene, the double bond's on carbon 2. And I've got a 2,3-dimethyl. So 1, 2, 3, 4. So I've got a methyl on 2 and a methyl on 3. So with this particular molecule being symmetrical, where this side is equivalent to that side, even if the bond stretches, so sometimes it would be shorter and then it would stretch. Sometimes the double bond would be a little longer. Since there's no dipole, the quantity of partial charge on the two carbons is exactly equal. Stretching it doesn't change its dipole. So that will not absorb any infrared light. That molecule does not give an IR signal. So when you're looking for carbon-carbon double bond signals, you will only see them if the molecule is asymmetrical. And that creates at least a small dipole for that carbon-carbon bond. If the carbon-carbon bond is symmetrical and there's no dipole, then there's no oscillating field associated with that dipole, and it cannot interact with the oscillating electrical field of the light, and so it won't absorb any light. So you want to look out for that a little bit. If a bond is nonpolar, it won't absorb any light. And so that relates to the second quiz question. Explain why a completely nonpolar bond will not give a stretching signal in the IR spectra. And the answer to that is, to absorb IR light, a bond stretch must create a varying or oscillating dipole. A nonpolar bond can't do that. And so it can't absorb any infrared light. Would you expect a CH bond to be doing that? Well, let's take a look. We just showed how this molecule was nonpolar. So is it true that a nonpolar structure won't absorb any infrared light? Not exactly. It's true that a nonpolar bond won't absorb any infrared light. So this carbon-carbon double bond is nonpolar, so I won't see a signal around 15 or 1600 for its stretch, where I might see normally a carbon-carbon bond stretch. But the CH bond is still polar, right? There's still a difference between carbon's electronegativity and hydrogen. So here we're not so concerned with molecular overall dipolar polarity. We're looking at individual bond polarity. If the individual bond is still polar, because one atom's more electronegative than the other, then if that bond stretches, there will at least be some oscillating dipole associated with that. It will be more polar when it's stretched farther and a little bit less polar when it's stretched closer or compressed. And so the change in polarity for the bond as the bond stretches and shrinks back down is what allows it to interact with the infrared light and absorb infrared light, causing a signal in the infrared spectrum. So I would expect to see if I looked at the infrared spectrum around 3000, wherever that is, I would expect to see a signal for the sp3 hybridized CH bonds, since they are slightly polar, stretching, and it would usually come, I'd see the signal down here around 2900, right below 3000, right where I normally see CH stretching on an sp3 hybridized carbon. So any CH bond should produce a signal, because every CH bond is at least somewhat polar. So it doesn't matter if the molecule is nonpolar. What matters is that the bond is polar, and so it will absorb some infrared light. Any questions about any of that? We also need to recognize that if I have multiple bonds of a certain type, they'll all produce small signals, right? So we just showed how the more polar the bond is, the bigger the signal. So all it takes is one CO double bond in my structure to produce a huge signal. Let's go back over here. Look at one of these OH, right? And that's what we saw here. OH bond is very polar. A big electronegativity difference between these two atoms means I've got very large partial charges, right? We already know that because we know OH sets up the hydrogen for hydrogen bonding. So it only takes one OH bond in my structure to produce a very big signal, because the more polar the bond is, when it stretches, the more light in that frequency will be absorbed. But why is the CH signal even bigger? The CH bond's not nearly as polar, right? One of these CH bonds, the electronegativity difference between carbon and hydrogen is not nearly as much as oxygen and hydrogen. So the reason that the CH bond is, or the CH stretch is similar, is because there are so many of them, right? Every one of these CH bonds is going to stretch. And that's going to cause a lot of different signals. And so if I have a lot of really small signals all in the same spot and they just add together, it produces one bigger signal. Right? So when signals overlap, they just add together. And that's what we're seeing there as well. So when you see a strong signal, it's either a sign that you have a very polar bond, or that you have a situation where you have multiple individual low polarity bonds that are all stacking on top of one another to give one big signal. And that's how certain breathalyzers work. So if you're driving all crazy on the road and you get pulled over and they do a breathalyzer, they're testing your blood for alcohol. They're looking for a specific IR signal. You breathe into the machine, it sends an IR signal through your breath, and if IR in a certain wavelength is absorbed, they know that you have alcohol in your breath. So why would it be a bad idea to focus on the OH as a way to determine if you have alcohol, right? This is a nice polar bond, big electronegativity difference, should give a big signal around 3400 in the IR. Is it reasonable to assume that if someone breathes into a breathalyzer and their breath absorbs infrared radiation at 3400 that they've been drinking alcohol? What's wrong with that assumption? Well, your breath better have water in it. Everyone's breath has moisture in it, and that also has an OH bond. So the signal around 3400 can be difficult to interpret. It either means you have an alcohol, or it means you have water in your sample. And obviously when you breathe into that, there's going to be a lot of water. So they can't be looking at 3400, or they would confuse water for alcohol. Right? Again, IR doesn't really tell you the molecule, it tells you about the type of bonds that are present. So because the ethanol molecule, which is the alcohol that's in alcoholic beverages, has a bunch of CH bonds that all absorb pretty close to 2900, that's where those machines focus on the whether or not there's a significant signal around 2900. You shouldn't have a lot of chemicals on your breath that or in your lungs that have that coming out of your breath that have a bunch of CH bonds. So that's what they focus on for breathalyzers. So the bigger the signal, the more of these molecules and the more of these bonds there are on your breath. So then next time, so obviously you want to do as much practice for those as you can, especially focusing on Chapter 8. So if you didn't get a chance to practice the recommended problems from Chapter 8 from last week, definitely do those. And let me know if you have any questions about that, if possible, before you take your exams this week and next Monday. And then look at practicing a little bit with some of the basic concepts for IR. Next time we're going to continue talking about IR. We're going to talk about the shape of the signal. So why are some of these peaks narrow and some of the peaks are more broad? And we're going to practice a little bit. So those videos should be helpful with that. And then we're going to talk about mass spec a little bit. Mass spec is spectrometry, which is a little bit different from spectroscopy. So we'll talk about that and what the differences are. And I think that should probably finish up Chapter 15 on Thursday of this week. So then next week we'll start getting into the NMR stuff, which you'll see is especially helpful in identifying the structure of different compounds. So please feel free to reach out anytime you have questions, and if that time is right now, just unmute yourself or type something in. I'll stay on the Discord for a few minutes to answer any questions anyone might have.